Yourself. If you know anyone else that needs one, feel free to grab it for them. All right, y'all. Test next week. How exciting! Again, I'll also be happy when test one is over, because that is not only an indication for you all how you're doing, but it's also an indication for me how I'm doing. So it's very useful feedback for me. See how we're doing, see how people are doing in various problems. So as I mentioned to you all, test next week, 22 multiple choice, and then the free response. Don't bring a Scantron. I will provide it for you. Literally, the last page will be the Scantron. The thing I'll tell you all when you get your test, first thing to do will be to tear off the last 2 pages, because one will be the Scantron, one will be the formula sheet. So that way you have easy access to them. Because at the end of the day, the Scantron is what I will collect, and then the grader will collect the free responses, and they'll go to 2 different homes. And then on the Scantron, I scan it with my phone. One of the things I like about that is it lets me look at a bunch of statistics on the problems. It lets me look at the problems and see individually which problems people did really good on, which problems overall didn't go so hot. So again, it gives me really useful feedback. Curving wise, it's always an interesting question. So, there is that statement that if everyone fails, no one fails. I don't know. At some point in my college career, I kind of landed on that statement. Maybe that's not true with some professors, but in general, that's usually fairly accurate. Professor's not going to fail anyone in the class, and I definitely won't. Because if everyone is failing something, again, there's only one common denominator to me. So, as far as curves are concerned, I'm going to look at, the overall percentage, how people did. But then really what I'm going to be looking at is the individual questions and seeing how people did overall in individual questions. If there's a question that very few people got right, say 20 to 30% of people got right, that's an indication that I did not prepare you all well for that question. In which case, maybe I just give everyone the points for that question. If the people got it right, they get those points plus the extra point. So that's kind of as far as curving is concerned. That's my philosophy towards it. My goal is not to reach a certain average percentage. My goal is that my test is a reasonable measure of what you understand. If my average is a 60, I think I've designed a poor test. Because if my average is a 60 and I say that's good, that means my expectation is that you all know 60% of what I've taught you, which is not a good measure. I would hope that you all know 80 to 90% of what I taught you. Another thing I want to mention about the grading. So as I've told you all, after test 1, I will actually move all the grades in. I think I mentioned this to you all. Your quizzes currently are graded out of 5 points. I need to move those so they're worth out of 4.5 points, meaning that boosts your things. Your clicker questions are currently... Move that guy. He's gone. Your clicker questions are currently graded out of all the points. I need to move those to a separate category that's worth out of 75% of the points. So whatever. I want to do all those things. But what I want to mention now that's new is that, to give you all some peace of mind, 50% of the grade, if you look at how the grade is broken down, 50% of it is iClickers, discussion sections, quizzes, and then this homework assignment. This homework assignment I'll mention on Tuesday. It's the physics I care about. Super easy assignment. If you do it, you'll get all the points. The point of it's not to have busy work. The point is honestly to have some separate assignment that's 1, easy points, like nice little grade booster, but 2, lets you connect what we've talked about to things that you're actually interested in, trying to understand how it applies to things you may interact with in a day-to-day thing. So I'll talk about that more on Tuesday, the physics I care about. That'll be due the week after the test. But that 50% is all the assignments, and then 50% of it is the tests. And if you do the math, if you get all the points on the freebie stuff, the clicker questions, the quizzes, the discussions, the physics I care about. So those are all just you put in effort. Those should be like 3 points effectively. They're effort-based largely. Then to get an A in the class, to get an A in the class, you just need an average of an 80% or higher on the tests. Because if you just do the math, it works out that way. So if you get an 80% or average, 80% or above average on the test, that gets you an A in the class. To get a B in the class, you literally just have to average 60s on the tests. That's how it works out. If you get that 50% free points and the rest of it is tests and you do the math, if you get averages of 60 or above, you basically get a B in the class, which it's fine. I'm fine with that. The reality is, if you've been putting all the work and gotten that 50% credit, that means you've been putting in work, and ideally that means you've learned it. And there's very few people that get all those points that don't also do well in the tests. So really, they should correlate. If you're doing all that effort, all those things I ask you to do, those aren't just busy work things. They're things that ideally reflect that you understand it, and then they correlate with good test performance as well. So, anyway, hopefully that takes some stress or burden off you all. There's some intentional design with how points are distributed in that way. But yeah, I expect good things. Last year when I taught this, grades were pretty solid, so I haven't really changed that much, so I don't expect things to change that much. Let's see. Actually, this may seem silly, but I have the test grades on here from last time. Test 1 was a weird one. I'm going to look at test 2. Test 1 was weird for some reasons. The average was, and it wasn't where I wanted it to be. It was okay. It was an average of 63, and I ended up bumping it up to a 75 based on a few of the problems. So the average ended up being a 75% after all was said and done. That tends to be where it's going to probably sit. So, anywho, there you go. They're behind the scenes grading things. All right, so we're just going to finish up these problems real quick. There's 2 problems on here I didn't finish. This is a great problem. Love this problem. It incorporates a lot of concepts together. These problems that use a lot of different concepts I really like, because if you can solve this problem, it shows you understand a bunch of pieces that we've talked about. What makes a problem hard in physics isn't usually the math. It isn't usually the equation. It's how many steps you have to do. And so these problems, this one is one that has a couple steps to it, so I like it. So we're going to do this one. We're then going to do this one. You don't need to know this one. I'll go through it very quickly because it's not going to be tested. But this is just tells you how you're charged for electricity. So it's just kind of fun to go through. It won't take that long. And then after that, I'm going to do an overview of everything we've covered. Hey, here are the main points of everything we've covered. It'll be a little wordy, but we'll get through it. It'll be a nice kind of summary of all the things you should be keeping what should be on your mind somewhere. If there's a topic that you're like, I don't remember learning that, that's a good one to look back on. Or if there's a topic I mentioned that you're like, ooh, this didn't go well, same thing. And then after that, we'll just start solving problems. I'll give clicker questions. They won't be worth part of your final grade. These are just kind of practice. I'm still going to use the clickers just because, again, it gives me feedback on how you're doing. Whereas if I just propose a question and say answer it in your head, I have no idea how you all are doing. So, anywho. All right, so let's solve this problem, y'all, without further ado. A heater is being designed that uses a coil of nichrome wire. That is just an alloy of nickel and chrome. You don't need to know that, but that's what it is. With resistivity of 100 times 10 to the minus 8 to generate 300 watts using a voltage of 110 volts. The wire is 14 gauge and therefore has a diameter of 1.627 millimeters. Fun fact, if you go buy a wire at a hardware store, it's given in gauge. The smaller the gauge, the thicker the wire. You don't need to know that, but it is a fun fact. When you go to the store and buy a wire, they will not tell you the diameter is this. It'll be 8 gauge, 10 gauge, 12 gauge. Smaller the gauge. And that's why I gave you all the diameter. How long should the engineer make the wire to accomplish said goal? All right. Looks like a lot, y'all. And so how do we take a lot of information and make it something manageable? We start the steps. We write down the givens. All right, so our first given, I was wondering why I'm stooping so much. We have the resistivity, 100 times 10 to the minus 8, with some units after it, ohms, meters. Actually, I'll give you all a second. See if you can jot down the givens. We're not in a rush. This is a good practice. There is 1, 2, 3, 4 givens in this problem. And the key to writing the givens is what variable do they go with? That's the skill here. All right, so we have resistivity. The next one is 300 watts. So that one's going to be power. P for power. The next one's a freebie. It literally says V equals 110 volts. So that should be free. There's 2 numbers left. Which one's actually useful? The diameter of 1.627 millimeters, which we need to convert. Whenever you're writing your givens, go ahead and just do the conversion now. Don't assume you'll remember to do it later. It's better to do it sooner than later. All right, givens. Awesome. See if you all can figure out what variable am I solving for. It says how long should they make the wire? What variable, what symbol are we solving for? It says how long. So there's a lot of variables for measuring distance, but we are so fortunate that in this case, when it says how long, it is going to end up being length. It's going to be an L for length. Now again, distance is one of those unfun things where there's like a million variables that go with distance. X, Y, Z, R, D. So many things. So that requires a little, like, if you're not sure which variable to use when it's talking about distance, kind of jot down something and then kind of go to step 3 and say, you can kind of start hunting through the equations. So if we're looking at length, there is literally only one equation I've given you all that has to do with how long a wire is. So that's the one you're going to want to look for. That's kind of how to choose an equation, is what equation even has. You can't solve for it if your equation doesn't even have that variable in it. So as far as what equation to use, it's most often motivated by the second step, what you're solving for, and you just find the equation that has the L in it. So let's pull up that formula sheet. You can see there's all the versions. Trust me, you all spend a lot of time studying for this thing. I spend a lot of time proofing this thing. All right, so we look at our big old list and we realize we are not going to use anything below this line. Every single equation on this is, the formula sheet I gave you is the one you're getting. Everything will be on there. But it is in the order that we learned it, so that's kind of nice. So it does group things. So literally you just hunt through this and find the only L that has to do with resistance. There it is. It's the only one with an L in it. So we know that resistance equals rho L over A. And we look at that equation and we say, cool. Okay, I need L, that's in there. Do I know the resistance? Nope. So, okay, I may have to figure that out. I know I'm going to use this equation. I have to. It's literally the only one with L in it. I've got no choice. So I don't know this. I do know rho. What about the area? And this is where you have to remember that additional fact. This is actually given on the formula sheet. I believe it is. Let's see. Did I give you area of a circle? Oh, did I not? All right, I'm going to add that too here because I'm so kind. Where do y'all want it? Should I put it with the physics ones or above it? Up top? Great. Look at that. You all are being part of the process. So this is the one. Okay. Unfortunately, I've already printed the exams. I forgot about that. But maybe I'll write it on the board or something behind me. Area of a circle is pi r squared. R squared. Okay. There's just no easy way to write that. I'll make a note of it or something. If you all remind me during the test, I'll give you the area of a circle. If you want to put it on your formula sheet, but I'll write it on the board up here during the test. I will give no context for it. I'll just say A equals pi r squared. All right, so that equals pi r squared, and we go, well, I don't have radius. And then you have to realize, oh, I got to do diameter divided by 2. Woo! All right, so cool. So we can calculate the area. We know the resistivity. We just got to figure out this R. So we ask ourselves, how can I find, given, based on what's given, resistivity, power, voltage, diameter, how can I find R? This is the thought process for solving a problem. This is the questions that you kind of ask yourself. So, see if y'all can find the equation that finds R. Based on having power and voltage, what equation will let me find resistance? And here they are in all their glory. Oh, I'm sorry. I didn't bring in all the ones that we did need. There you go. We need those bottom two ones. Oh, the capacitance one I stuck there too. Oh, it's there twice. That's weird. Great. Well, I hope you all know capacitance is Q over V because it's on here twice. You really know. All right. Again, the cool thing with power, there's literally only one equation that has power in it. There's only one equation that has capital P in it. So that kind of gives you also another hint of which one we're going to use. It's PIV. Now, if you look at PIV, you may ask yourself, but it doesn't have R. And this is where I'll remind you all, and I highly recommend you all put this in your note card, that you can take this and make 3 different forms with this. You can either do the algebra and do all that stuff, or you can have this on your note card. P equals I squared R equals V squared over R. P equals all of those things. And then you choose the one that's actually convenient for the problem. We're going to choose P equals V squared over R. We got V, we got P, we're solving for R. Okay? So again, this is an involved problem, y'all. There's multiple steps. This is what you can expect from a free response. A free response problem is not going to be a one-step problem. There will be a couple steps to it because it tests if you know. The multiple choice is, do you know that individual concepts kind of by themselves for the most part? The free response is, can you put them together? Can you do more than one step in a problem? Can you take one concept and connect it with another concept? So in this case, P equals V squared over R. If you rearrange this, I'll let you have the fun time of that. That's V squared over P. Again, you could put in the numbers and do the algebra, but to save myself a little bit of time, that's what it ends up being. I'll do it with the numbers because I like y'all so much, and that's what I've been teaching y'all. So we're going to take all this, move it to another slide, and at this point, y'all, steps 1, 2, and 3, that's the hard part. That's what you get most of the points for on the free response. Can you set up the problem? If I see that you've done all of this on the free response, if the grader sees that, that is a majority of the points. Because that is showing you wrote down the givens, you wrote down what you're missing, you found the equations. If you just flub the algebra, like sure it's going to affect a few points, but not much. Maybe this will get you close to like a 14 out of 20 or 15 out of 20, just this. Because it has all the physics in it. This is the physics. So, let's go ahead and move to step 4, start doing some things. So P equals V squared over R, we're going to start there. So 300 equals 110 squared divided by R. We're going to multiply R over. This is one of those algebra things that my high schoolers have been also when the variable's on the bottom, you got to kick it to the top. And then one last step, we'll divide that 300 over. If the variable you want's on the bottom, you got to kick it to the top. We don't want 1 over R. We want R. So get it out of the denominator. It doesn't like being down there. Well, I don't know its feelings. You can decide whatever feelings it has, but algebra-wise, it doesn't like it. So we get a resistance of 40.33 ohms. And again, the cool thing with step 4 is once you kind of set up how to do it, now it's just go. Now let's just put the things in and plug and chug. Step 4 should be, again, it's algebra, which depending on your feelings about that, but as far as this class is concerned, kind of ideally the easiest part. I didn't have to, ideally, algebra is something that you are feeling fairly comfortable with. I have no idea. Everyone's different. All right, so now we're going to take this equation. So we're going to take the R equals rho L over pi diameter over 2 squared. So remember I replaced, that rho is on top just to clarify that. I replaced area with pi r squared. and I replaced r with diameter over 2, because that's the definition of diameter. If that's something you feel like you're going to forget, put it on your note card. All right, so r, we just found that, 40.33 equals 100 e to the minus 8. That's rho. We don't know the length. That's the whole point of the problem. We know everything else. So my diameter is 1.627 e to the minus 3. Divide that by 2. Square that whole thing. Be very careful with your parentheses. And as long as you've written it carefully, you kind of have a guide for what to plug into your calculator. That's the reason for writing this stuff down. And so now when I plug in the calculator, I'm not trying to figure it out again. I'm just reading what's on here. So I'm going to simplify the right side. 100 e to the minus 8. No, e minus 8. Divide that by pi. Before you do any algebra, it's good, if you put the numbers in, like I did, it's good to simplify before you do algebra. Just makes less likely to make mistakes. And there's a lot to plug in here. But if I could show you my calculator, depending on your calculator, it can show you it just like what you type down. That's honestly the biggest benefit a graphing calculator has. It's kind of silly that they cost so much, because the biggest benefit they have is just a big screen that shows you what you typed. But hey, a scientific calculator will get you there. But yeah, I can see that what I typed down matches what I wrote down, so that's good. That's very helpful. So 40.33 equals 0.481 times L, and there's just one final step. All right. And I also, this is a good chance. Someone can confirm that. Did someone also get 0.481? If at least one other person did, that's a good sign. Okay, good. I got a few nods. Okay, I checked with that because there was a lot of numbers I just plugged in. Again, if you all messed up at this point, if you have done all these steps, but you accidentally plugged something in wrong, you will get an 18 out of 20. 90% of the points, because at the end of the day, I don't want to ding you for literally just putting it in wrong in your calculator. If you wrote it down correctly, that's what I'm testing. I'm not testing your ability to put things in a calculator. That's like the least important skill out of everything, though it is a skill that I need you to know. And we just divide these, but it is the least important. And I'm going to go ahead and put parentheses around this because it's a little weird to see. All right, and then yeah. And the cool thing is, if you have these numbers saved in your again, depending on your calculator, you can actually go up and reuse old numbers. So you don't even have to type them in again. That's also a great strategy. The less buttons you press in your calculator, the less likely you are to make a mistake. So oftentimes, if possible, I just literally go up, hit enter on the number I want from the previous one, and I get 83.855 meters. Cool. That's our answer. This problem really did not have that many steps. There's a few steps. But I really like this problem because, again, you had to take two different ideas, put them together. But at the end of the day, what does it boil down to? What's given? What's missing? Write the equations. Go from there. Again, a lot of these equations, y'all, you don't have many options. There's not many options for power. It's just P equals I. I mean, granted, it could equal those other things. There's literally only one equation with power. So if you see power, you know you're going to go there. If you see electric field, there's a lot of options, but they each apply to very specific circumstances. As long as you know what the circumstances are, you're going to know which one to use. The thing that you all are blessed with versus Physics 1 has to do with kinematics equations, which, if you remember those, good time. But even those really just boil down to what's given, what's missing, what equation has those. Like so I'm teaching that class currently, and it's still the same process. What's given, what's missing, what equation has those. So, and then we check if our answer makes sense. 300 watts isn't a ton of wattage. This is a fairly thin wire. So yeah, we're going to need a fairly long wire, 83.855 meters. That is fairly long, but you would actually be surprised how much wire is wound up in things. For example, we'll learn eventually about electric motors. There is so many winding. There is so much wire in those things. It's just all wrapped up. So if I did want to make more heat, though, I would probably make this even thinner, assuming it could handle it. So there you go. Cool. Love this problem. Great problem. Highly recommend doing it on your own. If you after the fact, make certain you know can do it without seeing me having worked through it all. All right. So this last one, I'm going to go much quicker. because again, it's not tested. I just want to do it for funsies. But again, it's not going to be tested. So I'm going to go through this one much quicker. There's not really an equation for this in the formula sheet. So again, don't stress this one. But still cool. All right, alternative CF bulbs and incandescent bulbs are LED bulbs. Everything's LED. LED is literally like better in every single way. It's cheaper to make. They last longer. They don't waste they use less electricity. LEDs are just like the best. So a 100-watt incandescent bulb can be replaced by a 16-watt LED bulb. Both produce the same amount of light. Great. Assuming the cost of electricity is 10 cents per kilowatt hour, how much does it cost to run each bulb for 1 year if they run for 4 hours a day? There's a lot of information here, but I'm, again, just going to kind of go through this real quick. So the wattage for, we'll call it the incandescent bulb I, is 100 watts. The wattage for the LED is 16 watts. And, the cost per kilowatt hour is 10 cents. This is literally something you can check on your power bill. There is a kilowatt hour cost. So like all these numbers I'm giving you, these are all real things that you encounter. If you buy a light bulb, it literally says how many lumens. If you buy a light bulb, it says how many wattage. If you look at your power bill, it says kilowatt. Obviously, it says how much it costs you at the end as well. So all of these are like super applicable numbers. So we're solving for total cost. Again, I have not given you all an equation for this, but here's how total cost boils down to, you know what, I'm just going to shove these together. It is the number of kilowatts you use. So whatever device it is, it's how much kilowatts it has, multiplied by the number of hours it's used, multiplied by the dollar amount per kilowatt hour. Okay? So this is all we're doing. We're going to figure out what's the wattage. We already have that, but we're actually going to convert it to kilowatts for some reason. That's just how they do it. Don't know why. Ironically, they don't keep things in base units. We're going to calculate how many hours it's used in a year, and then we're going to multiply that by cost, and that's it. So let's go ahead and do it. Let's do it for the incandescent. We'll just put I for incandescent. So the incandescent bulb uses 0.1 kilowatts. So I converted 100 watts to kilowatts. If you prefer, if this makes it easier to see, it's 100 times 10 to the minus 3. No, I hate that. We're just going to go with 0.100. That's how many kilowatts. How many hours this runs? Okay, so we got to calculate that real quick. Super simple. It says it runs for 4 hours each day. How many hours? So 4 hours per day. Just literally multiply that by how many days are in a year. Boom, we got the number of hours. That's how many hours it's going to get used for. 4 times 365. So that gives me 1,460 hours. And then last step, we just multiply that by that 0.1, the dollar amount per kilowatt. So you do all that math, we get 0.1 times 1,460 times 0.1. If you run an incandescent light bulb for 4 hours a day, which is not unreasonable. It's not unreasonable to have a light bulb on for 4 hours a day. In fact, it's probably on the low end. It costs you $14.06 for the whole year. Now, I'm going to quickly do a Google check because I have no idea what the cost is per kilowatt hour currently. This depends on what state you're in. This depends on what area you're in. Different states, different locations. There's all sorts of complicated things. So Florida, average cost per kilowatt hour. And let's hope that it gives me something. All right, 16 cents, according to a random website that popped up first. You know, how much can you choose? Yeah, 12 cents, 12 cents. They say 16 cents. Okay, so currently it's costing you about 12 to 14 cents. You can literally look on your power bill and see what it is. So, 12 to 16 cents is what it currently is, which is more than this. So if we just wanted to change that, we would just change that 10 cents to 14. Whatever. That's how much a light bulb costs per year, for good or for bad. An incandescent light bulb. An LED light bulb will instead be 0.016, because it's only 16 watts, times the exact same thing, So literally the only variable that changed is how much energy you're using per second. Everything else is the same. And you get it only costs you $2.34. So this is the difference. It may not seem like a big deal, but again, this is real numbers. Like everything I just gave you. In fact, the difference here would be more extreme. Well, actually, the difference may be... No, the difference would be more extreme if we actually use the real, if you change it to 15 cents. Every year, every single light bulb in your house, if they're incandescent and you change them to an LED that has this much wattage, depends on the LED you get. They're all different. You save yourself $12 per light bulb. You got 10 light bulbs, it's $120. It's nice. So again, it's just a cool kind of thing that connects the stuff we talked about. I like this problem. I'm not going to test you on it because it's a mixture of physics and economics, I guess. But your air conditioner is the biggest consumption for a few reasons. One, huge wattage to it. Like it uses a lot of wattage when it's running. Two, that thing's running 10, 12 hours a day. No other device in your house except your... Okay, so AC is the one that's... AC is the highest. Guess what the second highest is? Yeah, it's the one that's literally just running also all day. So there you go. How do you lower your power bill? You don't use your AC as much, but that sucks in Florida. So, but cost, it changes. All right, so we did it, y'all. So this is it. This, again, didn't need to know this per se. We've covered all the things. How exciting. So at this point, I'm just going to do a very quick overview. Not even a new slide, whole new PowerPoint. What have we covered in this class? And it's going to be a monologue. Pause me at any point if you've got questions, because I'm just going to be straight up monologuing up here everything we've covered so that you know what things to kind of keep in mind. So, test 1 topics. All right. This is also going to be a recollection of how much I remember, but I'm pretty confident in this. So, what's the first thing we learned? Charges and forces. So that's the first thing we learned. Charges. They exist. Sounds stupid, but that's literally where we started in this class. You got positive charge and negative charge. Protons are positive. Electrons are negative. And I will post these slides, so don't feel like you need to type any of this stuff down. I will literally post exactly what I'm typing here somewhere. I say somewhere. It'll be like in a folder called Test 1 or something. All right. Protons are positive. Electrons are negative. Everything is made of these things. You get a net charge when you have extra of one of them. If every object is made of protons and electrons, but you only get a net charge if you have extra. If I have 10 protons and 10 electrons, net charge is 0. You only get a net positive, net negative when you have different amounts. The charge of both of these, so the charge of a proton equals, again, this is going to be on your formula sheet, 1.6 times 10 to the minus 19 coulombs. The charge of an electron is the exact same thing, but with a negative sign. It's real weird, but that's just how things work. Have extra of one of them. Okay. And then, we talked about this. The equation for this one was Q net equals number of protons minus number of electrons times 1.6 e to the minus 19. This literally just says this part here, how many extra. Okay, and we've done some problems with that. Okay, so great, we got charges. So what? Who cares? Why does this matter? Opposites attract, like charges repel. Everything I'm mentioning is just purely observation. There is no, someone found these things exist, found that they repelled, found that they attracted. Basically, someone asked the question, why doesn't my finger go, I don't know if they asked this, but it is kind of the result. Why don't my hands go through things? More importantly, they knew these charges and they shot them near each other and they veered off. But that is ultimately kind of what it helps us answer. And Coulomb came along and he came up with that nice equation, F equals K, absolute value. I'm going to start to do a better job of that. Q1, absolute value of Q2, divided by the distance squared. Do not forget to square the distance when finding force. At this point, remember y'all, voltage, or I should say energy, is KQ1, Q2 over R. It's such a subtle difference. I can basically promise you all that I was a little mean, and if I asked you to find the force, I can guarantee you one of the answers can be found if you forget to square it. Why? Because there's literally, if you don't put the squared, you found energy. It's not that you just made a math mistake. You literally calculated something completely different. Like it actually calculates a different variable entirely without that squared. So it is a little mean, but just be careful with that, y'all. How do you make certain you're careful with that? I'm hopefully giving you all enough time. The goal is I give you all enough time. Go back and check your work. If you have the time, go back and literally just quickly calculate everything really quick. If you set up the math, plugging it back into your calculator takes no time whatsoever. It's worth a little bit of time. I can almost guarantee you if you do that, you will spot a mistake somewhere. Because you are making like 100 or more decisions on this test. Every decision is a chance for a mistake. You've seen me make a bunch of mistakes up here. It's going to happen. It's going to happen. Getting a perfect score is very hard. Not because the test is very hard, but because being perfect is just very hard. Humans aren't built that way. Robots are. They do the same thing every single time perfectly. We ain't built that way. All right, so great. F equals KQ1, Q2 over R squared. So if I have a positive charge and a negative charge, they're going to attract to each other. The force of this one will be the exact same as the force of this one. It doesn't matter which one. Great, and you got to do that. Now, nestled within this is you have to remember that this is a vector. Force is a vector, and therefore direction matters. You have to break the forces into X and Y components to combine them. That's something you all have to remember to do. Now, again, a lot of the problems, it'll either be all X or it'll be all Y. You won't have to deal with it. But if I gave you a problem that says, hey, I've got a charge here and a charge here, find the force on this charge. This is literally one of the problem set problems. The force of the top one on the bottom left one is down. The force of this one is this way. This is an X component. This is in the X. The other one's in the Y. You have to remember that to get the net force, square root of all the forces in the X squared plus all the forces in the Y squared. Don't forget about vectors, y'all. They were a thing we did. We had so much fun with them. We still need to remember them. So yeah. Forces and electric fields are the only vectors on this test. Forces and electric fields are the only vectors, and you have to treat them with the sensitivity that vectors deserve. If you want the angle, so what you can kind of do, if I take these two vectors, if I got that one down and that one right, we can see the total vector, I'll make it a different color, is going to be down to the right, F net. If you all want this angle, the angle, if it's that one, is tangent inverse of Fy over Fx. I'll let you all kind of remember, if you need that is a thing I ask. Not only do I ask you to find the net force, I often ask you all to show me what direction it is. It's one thing to know how much it is. It's another thing to know the direction, and direction matters a lot. The example I gave being, you could travel as fast as you want. If you're driving 120 miles per hour, you're not getting to Tampa if you go east. Direction matters. So, when it comes to forces, it matters a lot. All right, so there you go. Forces. Fantastic. 1 week down. That was week 1, way back when. It was a good time. All right, after that, we said, but why are these forces? These things aren't touching. Things have to be touching to affect each other. So we said, let's just make up something called electric fields. And something makes electric fields, all charges make electric fields everywhere. Everywhere. You don't need so if I have a charge, positive charge makes an electric field here, makes an electric field here, makes an electric field here, makes an electric field here. It makes it everywhere. Nothing has to be there to make the field, just like a gravitational field. Nothing has to be there. Now, which direction of these? So electric fields, they point away from positive charges, point towards negative charges. So electric fields point away from positives and towards negative. They point in the direction a positive charge would move. So if I instead drew a negative charge, and I said, what's the electric field here? It's going to point towards it. Whereas this positive charge, the electric field, points away. Okay? Okay, and then why did we make up these things? Electric fields cause forces on other, I'm going to underline that, other charges. A charge cannot affect itself. A charge cannot make a field that affects itself. If it did, it would cause a force on itself, which just would be really weird because that would push it in a what would that even mean? It would be zipping around randomly all over the place. It's just not how things work. So electric fields cause forces on other charges. They're everywhere. The second I put a charge at one of those places, the second I place a charge at one of those places, it will experience a force. So if I call this guy over here charge 1, and I call this guy over here charge 2, charge 1 makes an electric field to the right. Charge 2, the negative charge, will experience a force to the left. So that gets to the next thing. Positive charges move in direction of electric field. Let me be more clear. Positive charges experience force in direction of electric field. Negative charges experience a force in opposite direction of the electric field. Okay? So, that's also an important thing. Hey, you got an electric field? Because sometimes you'll have two charges, and one makes the electric field, the other experiences it. Sometimes, literally, there'll just be, hey, there's an electric field that way. I put a negative charge here. Which way is it going to move? And you don't see what's causing that electric field. Now, you can be kind of clever and think, well, what would make an electric field to the left? Oh, if I put a positive charge, it would make an electric field left. And then you can kind of, it's going to attract to that. Or you can just remember this rule. Or you can just have it written on your note card. So many options. Okay. And this electric field, so I should have put this, I'll put this up here. E equals KQ over R squared. The electric field due to a point charge is E equals KQ over R squared. So, actually, let's check that here. And then to that end, F equals E times Q. So that's the relationship there. That's the equation that goes with it. And then we did talk about flux. We talked about electric flux. I'll put both of those definitions. The main thing that you all need to know about flux, electric flux is the number of field lines, actually, is how much of the electric field passes through a surface. And so the equation for that was E equal, or, oh gosh, I'm going to have to look for the Greek letters. It was phi, capital phi. This is always the joy of teaching a physics class, is hunting through. There's Greek extended, Georgian, yep, all these very useful. There's Greek and Coptic. All right, so capital phi, bam, equals E, A, cosine, and I need another symbol, theta. So anytime you all see me put an equation here, just know this is the suffering I had to go through. All right, where E is the electric field, and then if I had a plane, boom, boom, and it had an area vector, Let's draw that electric field in the area vector. E, A, and I will move it so it's not literally over the words, and this is theta. Okay. Cool. So there was that. That was the thing we did. I am not going to be mean. You will not, do not expect a problem where I give you a surface like this, and I say the electric field is like this, and I give you this angle. You know, remember that when I had all those fun technical difficulties, and then I had to work it on the whiteboard, and it was a good time? You don't have to worry about that, okay? So don't stress that too much. Or at all. Just don't worry about it. Okay. I did give you a quiz problem where I said, hey, the angle between them is this, and it was just fairly straightforward, plug and chug. You had to find the area of a square. There's worse things in the world. All right. So, electric flux, electric fields, they cause forces. These are vectors. These are vectors. Bam, 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 bam. So don't forget that. All right. Now there's one more thing I couldn't fit on this slide, and that's the three different things that can make, other things that can make electric fields. So electric fields continued. So, point charges. So here's just a bunch of, so electric fields due to, and then I'm just going to kind of list them out. Point charges is, and this is where I'm going to start copy and pasting from the formula sheet. So for a point charge, it's that one. E equals kq over r squared. Already saw that. Cool. For a line of charge, I'll draw a picture of that in a second. So I'll draw a picture of these in a second after I get them all down. For a line of charge, it's this, and I'll talk about what sigma is in a second as well. For a plane of charge, this was a very important one because it comes up later in capacitors. It's sigma over 2 epsilon naught. And for a sphere of charge, we had two different ones. Oh, look at that. I was even so kind to tell you E in and E out. I didn't just put them both there. Blessings on blessings. All right. So, these are all in the formula sheet, but they're not labeled. This is what they look like. So, point charge already talked about. But here you go. Point charge, electric field, some distance r away. You use that one. Line of charge. You got some line of charge. Let's just make it positive. And you want to find the electric field some distance away? It's that one. Lambda is the charge per length. Length is how big this wire is. The plane of charge is a plane. A flat piece of paper, or, you know, just a flat something. Piece of paper is a good way to remember it. There is no distance in this equation. Super, 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 super important that you all remember that when it comes to a plane of charge, when it comes to a capacitor, distance doesn't matter. Remember, that was one of the really cool things, I call it cool. One of the really interesting, cool things about the plane of charge is somehow it doesn't matter how far away or how close you are. The electric field is the same everywhere. If it's 5 newtons per coulomb here, it's 5 newtons per coulomb here, it's 5 newtons per coulomb here, it's 5 newtons per coulomb, it's 5 newtons per coulomb everywhere. All right? But that's specific to the plane of charge. It's literally the only one that doesn't have an R in it. And then the sphere of charge, you got some sphere with some charge. If I'm some distance r, little r, inside of it, I use the inside one. If I'm some distance r outside of it, I use the other one. And the r, capital R, is the radius. And there's no like charge density here. It's all kind of built into this equation. Okay. So there you go. All our vector stuff. In my opinion, this is the hardest stuff mathematically, and it's got the most equations too. All right, 2 weeks down. And at this point, I'm going to save this because it would be very sad if it blew up on me. Cool. All right. Next, potential and potential energy. 2 different things. First things, these are not the same thing. I've said it a million times, so therefore I hope no one will make this mistake. Guarantee you someone will make this mistake. They are not the same thing. Potential energy is U. Potential is V for voltage. Not the same thing. So, charges have energy stored when there are multiple charges. There is a potential energy associated with that system. Sounds real fancy. It just says if you have multiple charges, they have stored energy. They want to do something. They have this potential to them. You got 2 positive charges, they want to repel. You have a positive negative, they want to attract. There's an energy, like, they want to move. They want to move if you have a few charges. That energy is U equals K. Now, this is a scalar. In fact, this is a scalar. So notice, I am not going to put absolute value on here. KQ1, Q2, divided by R. So energy of 2-point charges is U, technically sub E, for electric field, because you all learned about gravity way back when. The sign matters. Scalars, you need to put whether it's positive or negative. You have to. If you don't put that, you're going to get the wrong answer. Like, it matters, specifically, especially when you get to voltage. So there's an energy associated with the system. If you ever see the word speed or velocity in a problem, it is a conservation of energy problem. We talked about that, where the kinetic energy, the change in kinetic. In fact, let's just copy that over. The potential energy I start with equals the potential energy I end with plus kinetic energy. Yeah, there you go. All right. So that was kind of one of the things there. And then as far as voltage, voltage is not energy. So potential, electric potential, is also called voltage. Same thing. And this is that V equals KQ over R. It makes a potential everywhere. Positive charges go from high V to low V. Negative charges go from low V to high V. Okay? Everything wants to go to lower energy. Everything wants to go to lower energy. Voltage is not energy. Positive charges go from high to low. Negative charges go from low to high. And there's one last thing. I think if I make this tall enough, it's not going to look like too much. E equals VD. Or sorry, V equals change in V equals ED. Back to my Greek. Delta V. Delta is just the capital Greek letter, delta. Try deltas, it's for sorority. They're big on change. I'm really proud of myself on that one. But, yeah, delta V equals ED. For a constant electric field, which is the only type that you're going to interact with, because otherwise you'd have to integrate it. You're not going to have to integrate it. Woo. Okay. 3 weeks down. Just double, triple checking I've covered all the things. Yeah. So again, you can see as all these equations go. But yeah, there you go. On to week 4. And week 4 and 5 kind of go together, so that's kind of nice. All right, capacitors and resistors. Capacitors store charge when a voltage is applied. So C equals Q over V. They're literally like buckets for charge, but they're two parallel plates. So that's the next point. Capacitors are two infinite plates with opposite charge. So we get that equation. We get the same equation. Without the 2. There's 2 of them, so it's twice as big. Distance, or there is no dependence on location. Same thing as before. Doesn't matter where you're at inside of it. And then we said also C equals, nope, I'm not going to try to find epsilon up. Capacitance is also defined upon this, where I will draw a pretty picture for this. So if I have 2 plates, that's all capacitor is, plate 1 and then plate 2. And you know what? I'm not going to try to draw a 3-dimensional picture of it. We're just going to go with this because this is what they look like. The purple side's negative. This is a positive. I'll try to draw a picture. All right. That's something. The area. So A is area. And then D is the distance between the plates. D, distance between plates. Okay. All right. So this is like, there's a lot of kind of concept. So it only depends upon how the thing is shaped. The capacitance only depends upon how it looks. Now, there is technically the dielectric, but again, that's not going to show up in the test. I mentioned that to you all. It's a thing, but don't stress it for the test. All right? So just use it. That's why you don't see it in the formula sheet. Now, remember I did those 3 clicker questions in a row where I said, hey, this happens, what stays the same? Hey, this happens, what stays the same? Hey, this happens, what stays the same? If it's charged, charge stays the same. If it's connected to a battery, voltage stays the same. If I don't change the area or distance between plates, capacitance stays the same. So that's the whole, if I disconnect a capacitor, chuck it across the room, it still has the same capacitance, assuming I didn't break it. All right, so that's all the things about capacitors. Boom. Resistors will get its own slide, because that was kind of enough on there. So the electric field is constant. We kind of talked about that everywhere in it. All right, we're almost there, y'all. We're almost through a 5 weeks worth of physics. Wild. In 8 slides. All right, so resistance is defined as how much an object resists the flow of electricity. The equation for it was going to get copy and pasted as well. So R equals rho L over A. We just used that in class today. And so rho, that little P that I'm going to have to totally copy because it's not P, it's rho, it's the Greek letter rho. Resistivity depends on material. L, length of wire. A, area of wire. So draw a sweet picture of that. Wire, area, length, resistivity is just what material it is. All right, super simple. As temperature goes up, resistance goes up. Just a fun fact to keep in mind. And then, that's it for resistors, really. We're going to talk about Ohm's law and P equals IV, but that's it for that. Fairly straightforward. They resist things. All right, the last one. Ohm's law and power. V equals, okay, so we have to define current. Flow of positive charges, hate it, but per unit time. It's actually negative charges flowing. All right. Ohm's law, V equals IR. Power equals IV equals I squared. Nope. Let me end this where I'm starting to rush, which is always a bad idea. Yep, it is I squared R. I'm so eager to be done with this review. I love you all, but monologuing for this long is not fun for me either. It's my worst thing when high school teaching as well, but when it comes to like just literally going through all the stuff, it's just how it goes. When we solve problems, it's going to be a bit more back and forth. So like in the last little chunk of class / next time. Okay, so that power is the energy used per second. Unit is watts. Worth mentioning that because people tend to forget that. That's it. 5 weeks and 35 minutes or so. 7 minutes per week, that ain't bad. So all of this will get posted in all its reviewy goodness. So this is a great kind of checklist of concepts that you all need to know. And looking through those and asking yourself, do I remember how to solve that? Do I remember how to solve that? Have I solved problems that involve that? Because every single one of the things I just put on here is free game for questions. Every single thing here is either a concept or a math problem. And if at any point you look at one of these things and you can't even think of a problem that would involve it, you should find a problem that involves it. Because there is one out there. Either it's a clicker question, either it's a problem set problem. But I've kind of given an example, either mathematically or conceptually solved every single one of these things. So, now what do we do? Now I ask you some clicker questions because they're a good time. I mean, yeah, Tuesday we'll get more into the math thing, but let's do some of those clicker questions because I think these are the ones that kind of trip people up the most. So, what happens to the capacitance if I triple the area and half the distance? Does the capacitance, my new capacitance, is it 2/3 my original? Is my capacitance 3/2 my original? Is my capacitance 2 times my original? Or is my capacitance 1/2 my original? You know what? Let's get spicy. Let's say it's the same. All right, we'll do one of these. And then honestly, I started doing this one. Oh, that's my high school email. What do y'all think's going to happen? We'll do this one just to kind of give you all an example of what I'm talking about. And then I've kind of changed my mind. I'm just going to ask you all what you want me to. So we'll do this one clicker question, and then I'm literally just going to take questions from you all for like what may be confusing. We'll do this one real quick just to give you a sense of what I mean by the clicker questions that you should go over. The math problems, there's millions of examples, but this is one of those. Oh, I did terrible. This is what happens when you make a problem on the fly. Let me give you all so that we're going to change a bunch of them so you have no idea what's the right answer. You'll never know. Every single one's getting changed. Sneaky, sneaky. And then everyone's going to online, or people that aren't here are going to freak out because they're he wasn't going to ask clicker questions. And then they get bombarded with one in the last 15 minutes of class. It's not worth any points, though. All right. Oh, look at y'all. Doing so good. This is a great, again, I can guarantee you there will be a few problems like this where I say, hey, I do this, how does this affect blank? Guarantee you. And I've asked a bunch of these. So there's a lot of examples to kind of practice with. All right, we're going to go to 15. So 5, 4, 3, 2, 1. All right, just for no suspense, bam, it's that. Y, C equals epsilon naught A over D. So my new one, if I triple the area and I half the distance and you pull that to the front, 3, if it's on the bottom, that's going to become a 2. That's 6 times the original. All right, so that's that kind of idea. Those are great problems. They always trip people up. Okay, enough of that. What questions y'all have? What are you worried about? What are y'all concerned about? I mean, I sent out the survey, but how are y'all feeling? All 20 of y'all. So many. It's cozy again. Let's take a seat. Give me a thumb. How are you all feeling? You're my slice of the class. You're probably more than okay. Ups, down, sideways. And it's okay. It's okay to not be feeling good going into this. Do you all feel like you know what you need to do? Do you know what to look at? Or are you concerned? I'm not sure what things I should look at. If so, let me know. If you're like, man, what do I look at? Okay, feeling good about that? Okay. How y'all feeling about vectors? Oh, yeah.
I was going to say, can we do vectors?
We will definitely do vectors. Tuesday, I will devote at least several problems. Yeah, Tuesday I'm going to spend the time working out those. Because, I think if people make mistakes, that's going to be a big one. I will say, vector-wise, problems to think about this weekend, so that way you're not waiting till Tuesday. So this is a good point. I can do this. What are some really good problems from the problem set that I'm if you do this yourself. So the one we did today, that's a really good problem. The one with the wire, how long it is, love that problem. Fantastic problem. Tests a lot of things. Really good one to solve through. I love this problem. And the 4 cases, rank the force, so put a positive charge here. Love that problem. Why? Because it tests 3 different things simultaneously. 1, so if you put a positive charge here, you have to know the direction of forces. So you have to know which way it's going to get pushed or pulled. You have to know, in addition to that I treat each of the charges by themselves, and I find the force due to each one, and then I have to combine them together. So for example, this first guy here, this is a positive charge. It's getting pulled to the right by this one. It's getting pushed by that one. So the net force is the combo of those two. Love this problem because, and then also if we look at a later one, let's look at this one right here. If I put a positive charge here, it gets pushed by the one closest to it, and the one away from it pushes it but less because it's distance dependent. So that's a really good concept. There is 0 math there. Love that problem. So that's a really good one vector-wise. And again, you can see the answer there. This one and this one are fantastic to do. If you can do this guy or gal, I don't know if it's nicer to call it either gender. If you can do this one, this box, and find the force on one of those, you're good at vectors and electric field. This is beyond, this problem takes a little bit too much time to ask you all to solve. But if you can do this, it's not going to be any worse. Nothing, it won't be worse than that. Okay, so I like that one a lot. Let's see. Okay. Look, this one sucked mathematically. So there was the two problems. If you all remember, it's that one, so back when. Two charges placed fixed apart. Where should I put charge 3 so it experiences no force? I will not ask one this bad, but I like this problem. I quizzed you all on it because I like that problem in the sense of it tests a bunch of different things. If you can do that one, that's awesome. That means you understand a lot of different things. Do every version of that problem. If you all didn't realize, there's like 3 versions of that. When you get to electric field, there's another version like that. Love that, because again, it tests so many things. Fantastic one to look at. When you all are looking at your problem sets and you're trying to decide what you should study, ideally you should not need to solve every single problem again. Because ideally, you've solved all these before and look through them. If you're like, yeah, I remember how to do this, move on to the next one. Do not actually work out all 60 problems again, unless you feel like you need to and you haven't done that yet. But ideally, you're going through these, and if you spot one that you're like, wait, I don't remember how to do that, quickly start like setting up the problem. If you can set it up, move on to the next one. You don't need to actually numerically solve every single one of these. You should only completely solve a problem if you really don't know how to do it. Otherwise, if you can set it up and you're like, yeah, okay, I remember how to do this, on to the next one, on to the next one. My hope is at this point that you ironically shouldn't have to study much because you've been putting all the time in up to this point. And so it should just be review versus having to learn it for the first time kind of thing. So my hope for you all is that as you go through this, you're going to realize, I know this, I know this, I know this. And if you have that feeling, that's awesome. If there's things that you don't know, skip those, do those problems. Shoot me emails if you're confused on any specific spot. So again, like that stuff, again, all these are kind of decent. They're solid to do. Just quickly look through them. Set them up. You don't actually have to plug in all the numbers. But hopefully you'll find at this point. All right, I love the, make certain you can do a conservation energy problem. There's quite a few of those. Make certain you're comfortable with. QV equals 1/2 mv squared is what they basically all boil down to. Oh look, another one of those. 2 charges, 0.5 meters apart. Where does the potential equal 0? Yeah, that's again, great one. Sure, again, make certain you can find potential due to more than one charge. Yeah. The best recommendation, honestly, I can make to y'all, make certain you can set up the problem. You don't need to solve every single one of these numerically. Please, sounds terrible. I'll straight up tell you all, the reason I designed my class this way is because this is how my graduate electrodynamics course did it. He gave us a packet of problems, 60 problems. He pulled homework problems from those. And it was a very nice, so literally what we would do before the test is we'd get together and we'd just go through the thing. And by the end of that, and we wouldn't solve every single problem. We would look through it and say, what's a reasonable problem for them to ask? An unreasonable problem is one that takes 20 to 30 minutes, like 30 minutes to solve. I'm not going to ask you a question that takes 30 minutes to solve, y'all. You ain't got time for that. My expectation is if you know what you're doing, you should be able to solve the free response problems in 10 minutes. If you're taking more than 10 minutes, that's okay. But that's kind of my expectation of difficulty-wise. As long as it's if you know what you're doing, free response should take you 10 minutes, less, 5 to 10 minutes. Which sounds kind of short, but really I give you all the time so you can process it. But ideally you look at it and you say, yep, this is what I need to do, and you start working through it. And that'll take you 5 to 10 minutes, including all the writing. And that's the longest problem I give you is the free response. Every other problem, if you know what you're doing, less than 1 minute. There's not that much writing for most of them, for the multiple choice. All right. So yeah, go through these. Have fun. I say fun. Again, I really hope when you all look through this that you're not like, oh crap, this is so much, I don't know any of this. My hope is that you put in the time already and you look at this and you're like, oh, I know this. I know this. I know this. I know this. That's I hope that's the feeling that you have when looking over this. So you can come into it not stressed. Because I can guarantee if you can solve these problems, you will ace my test. Along with the clicker questions. Make sure you look through this. All right. Any last questions? At this point, it's just me blabbing. All right. If you have any more questions, I'm here. I will be here as long as need be. So. I'm sorry, y'all. I'm so to earn my 5 minutes of time, I will stay here till 5:50 for individual questions. But at this point, I don't think there's much more I can do that'll be helpful for as a whole. Knock it out, y'all. Shoot me emails. We got time before the tests. If you have comments, questions, concerns, I obviously can't help you with a million problems. It's a little bit too late for that, but individual ones, sure.